Hello and welcome to this workshop on logistic regression in R. So logistic regression is a really useful tool for modeling data, which is sort of the other way around to what we're used to, the kinds of experiments that we tend to do in the lab, where typically we might have predictor variables which are factors. They're categorical. It might be vehicle versus treatment. And our dependent variable, the thing that we measure as an outcome, is a continuous variable. Logistic regression handles models or experiments which are the other way around. So where our predictor variables may be continuous, and our outcome variables might be categorical. So an example being that we may measure lots of different things about individuals and use those variables to predict whether a person will survive or die, whether they're positive for an infection or not, or even whether or not they will default on their mortgage, for example. So logistic regression is sort of the other way around, where our dependent variable is categorical and our independent variables can be either continuous variables or categorical variables, and we'll talk about both examples in this tutorial. Logistic regression can be binomial, and what we mean by binomial logistic regression is that our outcome variable has two levels. So it could be survive or die, positive, negative, etc. Another form of logistic regression is multinomial logistic regression, which we'll touch on just at the very end, where instead of having just two categories, as the name suggests, we have more than two, and this could be 3, 5, 7, as many as you'd like, but we'll see when we come to it that actually multinomial logistic regression is, at least in my opinion, not always as useful as binomial logistic regression, and the more categories that you add, the less interpretable the result becomes, and there are other techniques, I think, which are probably better at dealing with this kind of model than that. There's a third kind of logistic regression which we won't talk about today, called ordinal logistic regression, which, as the name suggests, the categories of the dependent variable have an order to them. So, for example, we could use it to predict the likelihood that someone will progress from disease stage 1 to disease stage 2. So the levels of the dependent variable have an important order. So before we carry on, I recommend that you've watched at least the first introduction to R tutorial, just so that some of the commands that we're using make sense and you know how to navigate R. But other than that, let's get stuck in. So let's download some example data, which should be available to you. So we're going to create a data frame called MyData using the read.csv function. Something that we haven't talked about before is that the read.csv function can actually read data files from a web server. So there's some publicly available data at the following address. So it's https://stats.idre.edu/data/binary.csv. And if you hit Control Enter, then R should retrieve that data from that server and save it in an object called MyData. And then we can explore this a little bit just to have a look. So basically, we have a data frame with 4 variables. Admit, which is whether or not a student was admitted to a particular university. So 0 means that they weren't admitted, 1 means that they were admitted. GRE, which I'm not entirely sure what this stands for. GPA stands for grade point average. So it's a measure of the student's performance. And finally, a variable called rank, which is a ranking system where if the university that the student applied to had a rank of 1, this was the most prestigious university, all the way down to 4 as the least prestigious. So if we look at the summary of our data frame, then we get some summary statistics. And notice actually that both admit and rank here have been considered by R to be continuous variables because we get our summary statistics for them. But actually, they are both factors, where admit has 2 levels, 0 and 1, and rank has 4 levels, 1, 2, 3 to 4. And we'll deal with that in a second. Finally, we can also have a look at the structure. And the additional information that this tells us is that R considers these guys to be numeric vectors or integers, and that we have 400 observations of 4 variables. So we want R to consider the rank variable as a factor, and so the way to do this and I'll explain why it's important that we do this later on, is we basically overwrite the vector rank, the column. So we give the data frame the $sign to subset the rank column, and then we're basically just going to overwrite this. And we're going to overwrite it with exactly the same data. We don't want to modify the data, but what we're going to do is wrap it in this function factor, and what that does is turns this vector, which we can print, turns this vector into a factor. So if we run that and then call the vector again, we can see now that we know it's a factor because at the very bottom prints out the levels. It has 4 levels, 1, 2, 3, and 4. For the purpose of this demonstration, we're going to alter the data a little bit just so that the tutorial works out a little bit nicer and makes a little bit more sense. So what we're going to do is take every student who was admitted to the university that they applied to and just increase their GPA by 1, just to make the example a little bit easier. So we're going to say take the my data frame, and we're going to subset and select all of the cases for which admit is equal to 1, and we want to select the GPA variable, which is column number 1, 2, 3. So what this does is selects the value of GPA for every student who was accepted into their college, and we're going to this value, we're going to reassign the identical value plus 1. So if I print this out again, I hope that you can see that we've just, for every single student, we've added a value of 1 to their GPA. So this is just for the students who were admitted into their university of choice, just so that we can separate out the two groups a little bit for the sake of this tutorial. Okay, so let's plot our data just to understand the relationship between the GPA variable and whether or not a student was admitted into their university of choice. I'm going to do this using ggplot. So if you've completed the ggplot tutorial, then please feel free to follow along. If not, then don't worry about this too much, because it's just for the purpose of demonstrating exactly what we're doing with logistic regression. So I'm going to plot my data. I'm going to plot GPA on the x-axis and admit on the y. And we're going to add some points. So each dot is a different student with their value of their grade point average and whether or not they were admitted into their university. So 0 is, so these guys down here were not admitted, and these guys up here with the value of 1 were admitted. Now we could model this relationship using a linear regression model, for example, and we can have a go at doing that, we can do that in ggplot using Jom Smooth. Tell it to use a linear model method. I'm also going to tell it not to plot standard error curves, and I'm just going to limit the plot so that we only see what we need to see. Okay, so we could model this relationship using a linear regression model, as you can see here. And it sort of works in a way. You can see that as GPA increases, so does the likelihood that a person will be admitted into university. But the model isn't a very good fit, really, and is violating some of the assumptions for a linear model, such as homoskedasticity. So let's model this instead using a binary logistic regression model, and we can represent this in R, in ggplot, sorry, by telling it that we want a GLM model. This stands for generalized linear model. I'll explain a little bit about this in a second. We don't want standard error bands, and method args again, don't worry if this doesn't make sense. What we're basically asking ggplot to do is plot our data and plot a binomial logistic regression line on top of our plot. And so this is what we'll be modeling with our logistic regression model. And you can see that it sort of models the data a little bit better. And basically the way that this works is that we build a model, so in this case, predicting admit from GPA. And in this two-case scenario, if our value of GPA is modeled such that if we have a value of GPA which predicts a value of admit closer to 1 than to 0, then for that individual we would predict that they would be admitted to college. Whereas if an individual had a GPA value which predicted a value of admit which was closer to 0 than closer to 1, then for that individual we would predict that they would not be admitted into college. So let's actually build our model formally so that we can have a look at our model coefficients and work out sort of exactly how much more likely you are to be admitted into university with a 1 unit change in your GPA. I should mention, by the way, that this is completely false data and is not based on real relationships. So we can model admit by GPA. We'll look at the other variables in our data table in a second, but for now we'll just focus on GPA. So we're going to build GPA model. To this object we're going to assign our model object. So you'll recall that from, at least if you did the second introduction to R tutorial, that if we want to build a linear model, so this could be a regression model or an ANOVA, two-way ANOVA, or even a t-test, we can do all of these through the lm linear model command. Linear models are a sort of, think of them as a subclass of generalized linear models. So for linear models, the relationship between your outcome variable and your predictor variables is linear. For generalized linear models, they can be non-linear. So for example, in this case, the logistic model. And so for this case, we can build the model using the GLM function. But the way that we specify our model is very much similar to how we did with the linear model command. So we give it our output variable, admit. And this is dependent on GPA. This is our model formula. Our data is equal to my data. and this is the important bit, the family. So this basically, so there are lots of different generalized linear models, so from binomial logistic regression, multinomial logistic regression, Poisson regression. So to tell R that of this family we want a binomial logistic regression, we simply say family equals, and then in double quotes, binomial. And if we hit Control Enter, we've created our model. And if we have a look at our model using the summary function, GPA model, then we get some output statistics. So first of all, we get our call. This is our model formula that we just specified a second ago. And we get a table of coefficients and some p-values. So how do we interpret these? So these estimates that we get, the intercept is probably not so interesting, but the estimate for GPA, this is the log odds for every 1 unit increase in GPA, the log odds of being admitted to university increases by 8.71. But nobody can think in log odds. I can't understand exactly what log odds are. And one of the reasons why clinicians like logistic regression so much is because you can derive odds ratios from these log odds. And an odds ratio is a much more interpretable way of understanding the relationship between the variables in your model. And we'll explain these and how to interpret them in a second. We also get a p-value for this, so the relationship between GPA and whether a student was admitted to university or not is highly unlikely to be stochastic. It's likely to be predictive of whether a student will be accepted to university. Now we can use this function coef for coefficients to get the coefficients from the model, and you'll notice that these coefficients are the same as here, so 8.71. So this is the change in log odds for every 1 unit increase in GPA. To derive odds ratios from log odds, you simply take the exponent, so exp. So to take an exponent is to do the opposite of to log. So an example would be the exponent of log 23 is 23. So the exponent is the reversal of a log function. And so if we take the exponent of the log odds from our model, then we get our odds ratios. So an odds ratio is a ratio of odds. But the way that we interpret this in terms of our model is for every 1 unit increase in GPA, the student was... So this example is a little bit ridiculous because we changed the values earlier to make it a little bit nicer. But for every 1 unit increase in GPA, a student is 6,049 times more likely to be admitted to university than not. So that's how we interpret an odds ratio. Now, usefully, we can get confidence intervals for our odds ratios, and we can use this. We can do this using the confint function. Now, if we do this, these are not the confidence intervals for our odds ratios. These are confidence intervals for the log odds. And to get the confidence intervals for the odds ratios, we simply do what we did before and wrap this command inside the exponent function, and then we get our confidence intervals. So the lower is 789 times more likely, and the upper is 94,759 times more likely. So quite a wide confidence interval, but clearly highly predictive in our model. Now, I mentioned earlier that In logistic regression, your predictor variables can be continuous, but they can also be categorical. So let's build a model now where we predict admission based on both categorical and continuous variables. So we'll create a full model, again using the GLM function, and this time we want to predict admit based on GPA and GRE, which I'm still not sure what the GRE variable stands for, sorry, and rank. Data are my data, family equals binomial. And just like before, we can call summary on our full model. And again, we get our call. And now we get our coefficients for each of our predictors and their p-value. So we get an estimate for GPA and its p-value. We get an estimate for GRE and its p-value. And then notice that something interesting has happened. For rank, which is a single variable, we have 3 coefficients. And the reason for this is that rank is a factor with 4 levels. And so these coefficients are each comparing the log odds of being in rank 2 versus rank 1, or rank 3 versus rank 1, or rank 4 versus rank 1. So rank 1, as it's the first level in our factor, has been taken as a sort of reference baseline level to which these are compared. Now this is happening because earlier we told R to consider rank as a factor. If we hadn't have done that, we would have got a single estimate for rank, treating it as a continuous variable, which we would have interpreted as for every 1 unit increase in rank, a certain log odds change in admission. So the way that we interpret this is that the log odds of admission decreases by 0.287 as we go from rank 1 to rank 2. The way that we interpret this is that the log odds of admission decreases by 1.423 as we go from rank 1 to rank 3. And so basically what this is saying is that the higher the rank of the university, the less likely the individual is to be admitted. Although none of these are actually significant in our model at the moment. Now again, I'm not very good at interpreting log odds. I think few people are. And so let's steal this from up here to have a look at our odds ratios. Let's change this to full model. Full model. And so for GPA, for every 1 unit increase in GPA, a person is 7,318 times more likely to be admitted. For GRE, the odds ratio is smaller than 1, which in of itself is a little bit of a difficult thing to interpret. The way to interpret odds ratios smaller than 1 is to, if we do 1 divided by, and copy the odds ratio, is to say it's sort of the other way around. For every 1 unit increase in GRE, a student was 1.005 times less likely to be admitted to their university. Now notice that for GRE, this odds ratio is very, very close to 1. And the reason this is because a 1 unit increase in GRE is actually very, very small. So these GRE units are sort of in the hundreds. And so although it's significant, you would almost be tempted to conclude that there's no real effect of GRE, because 1 unit increase in GRE changes the odds ratios by very, very little. You might think that, well, this is, a person is no more or less likely to be admitted to university really for every 1 unit increase in GRE. But the problem is that actually a 1 unit increase in GRE is very, very small, because these values are sort of in the hundreds. And this is an important point to raise, because if the scale of your if a 1 unit increase in your variable is kind of meaningless, either because it would be a huge increase in that variable, or in this case a very, very tiny increase in that variable, it can often be much more intuitive to instead of entering the raw variable into your model, enter the log2 variable into your model instead. And we'll do this in a second, but basically how you would interpret that then is that for every time the variable doubles, then this is the odds ratio that you'll be given. Similarly, the odds ratios for the levels of rank are all smaller than 1. And so to make this a little bit more interpretable, we can do 1 divided by the odds ratio. And the way that we interpret this is that if the university was ranked number 2, a student was 1.33 times less likely to be admitted than if they had applied to a university which was ranked number 1. And then the similar things will apply for universities ranked number 3 and number 4 as well. And again, we can get our confidence intervals for all of these odds ratios. If we want as well, that we can combine these into a slightly nicer table using the cbind function. So if we say OR for odds ratio equals this, and then supply the confidence intervals which come with their own headings, and if we hit Control Enter, then we get a slightly nicer table where we have the variables entered, the odds ratio for each of them, and our lower and upper confidence intervals for them. Now, I mentioned earlier that we can log2 our predictor variables to make their odds ratio slightly more interpretable, and so I'm going to do that with the GRE predictor in our model. And we can simply do this in the model call by using the log2 function and wrapping it around the GRE variable. And if we rerun this and have a look at our coefficients, if I do 1 divided by the odds ratio now for the log2 GRE predictor, this is slightly more interpretable. So how we interpret this is that every time the GRE variable doubles, a student is 8.72 times less likely to be admitted to university. And we can get confidence intervals for these again, and build our table to make it slightly nicer to interpret. So I hope that makes sense in interpreting odds ratios. So if the odds ratio is positive, you simply interpret it as a 1 unit increase in the variable means that a person is this many times more likely to be admitted. And if the odds ratio is smaller than 1, then a simple transformation helps. Just dividing it, 1 divided by the odds ratio allows you to interpret it the other way around. So for every 1 unit increase in log2 GRE, which of course is a doubling in GRE, that's why we use log2, a student is 8.72 times less likely to be admitted. Now, in our model, we get individual odds ratios and p-values for the different levels of our categorical variable rank, comparing them back to our baseline, which is rank 1. But actually, we may want a single p-value to compare whether the predictor overall contributes to prediction of whether a student was admitted or not. And we can do this using the AOD package. So remember, we can install the packages using the install.packages function, and we're installing the AOD package, and then loading it into memory using library. And then the function that we want is wald.test, and it has this argument called b, to which we need to give the coefficients from the model. It has an argument called sigma, which requires something called the variance-covariance matrix of our model. Don't worry if you don't understand that. And we need to tell it exactly which terms in the model we want to compare. And basically what we need to tell it is we're asking whether terms 4, 5, and 6 significantly contribute to the model. These are 4, 5, and 6 because we count the intercept as 1. So this is 1, 2, 3, 4, 5, and 6. So we say terms equals 4 to 6. And if we hit Control Enter, then we get our wald test, where our p-value is much larger than 0.05, and so we would conclude that the rank of the university doesn't significantly contribute to our model. And so actually we could alter our model now and say, well, let's remove rank. We know it doesn't contribute to the predictive value of our model, whereas both GPA and GRE do. And so we can just recreate our model using just the parameters that we know significantly contribute to it. So we've got our final model, and we find that both GPA and the log2 GRE are able to significantly predict or contribute to the prediction of whether a student would be admitted to university or not. But once you have your model, it's important to assess whether or not your model is generalizable, whether you've just overfit your point, so that perhaps you could have some sampling error in your sample such that your model fits your data very well but just doesn't generalize very well to the real world. And so perhaps if you then went in and gathered more data, perhaps your model wouldn't fit that data very well. And a way of guarding against that, of working out whether your model does generalize well, is by something called cross-validation. And we're going to use a version of cross-validation called k-fold cross-validation. So cross-validation concerns splitting your data set into training sets. So a training set is a subset of your data which you build the model on, and a test set, which is a subset of your data set which you apply your model to, the model that you built from the training set, and see how well it fits to your test set. And the principle is that the students or the observations that are in your training sets are not in your test set, and vice versa. Now, k-fold cross-validation is a version of cross-validation which basically works as follows. So the first time that you perform a cross-validation, you randomly select a subset of your observations, which are going to be your test set, and the rest are your training set. So here at K1, we just look at the data in the green bars. We build our logistic regression model based off this data, and then we apply our model to the test set of our data and see how well our model is able to predict whether a student was admitted or not. And then we do it again, but this time we pick a different subset of our data to be our test set and training set. And so we build our model based on the data in the green boxes, and then we apply our model to the grey and see how well it's able to predict whether a student is accepted or not into university. And we do this again and again and again, a certain number of folds, and so this is why it's called k-fold cross-validation. And the model that we get from each time and how well each model is able to predict group membership for the test set is saved. And so at the end, we're able to take sort of an average model and see how well across all of these different folds, how well our models are able to predict the correct values. If we had a model which, based on our training data, was not generalizable, was only able to predict the data, was too specific for our training set, and wasn't able to predict very well in the test set, then this would mean that our data are insufficient really to be able to build a model that is sufficiently predictive and accurate enough to predict real-world scenarios. So how do we perform this in R? So there's a handy package that we're going to install called Caret, which handles most of this for us. I should say as well that cross-validation is not something that is specific to logistic regression, but is something that really, if you're building models to predict, particularly models to classify, then cross-validation is always an important step at the end of your analysis to make sure that the data that you have allow you to are sufficient and a good enough sample of the population to predict from unknowns. So we're going to install Caret package, not spelt like the vegetable, and then load it into our current R session when it's done. Okay, so before we can perform the cross-validation, we just need to tell Caret a few settings, basically, exactly how we want it to perform. So we're going to call this cross-val settings. And to set these, we're going to use a function in Caret called train control. And all this function does is allow us to set our settings and preferences for the cross-validation process, which we'll use in a second. So there are lots of different ways of performing cross-validation, and the method that we're going to use is repeated cross-validation. And what this means is that we'll perform cross-validation once, and then again, and then again, and then again, and we'll repeat it k number of times. The number of times we're going to repeat it is 10. This value is sort of arbitrary, but if you look on line, 10 seems to be a decent number of iterations to perform. And then there's an argument, save predictions equals true, which basically just means that every time it performs a cross-validation, it will save the result of the model, and it will save the accuracy of the model as well. So we run this, and now we can actually perform our cross-validation. So let's call this cross-val. We're going to use the function train within the Caret package. And inside this train function, we're basically going to specify the model in a similar way like we did within the GLM function earlier. Now it's a slight quirk of this function that whereas before we didn't need to specify that admin was a factor, the GLM function was smart enough to know that it was a factor. For the train function, we need to specify that it's a factor. So we're going to use this function as.factor to wrap around admit. So this is our dependent variable. And again, just like we specified our model, this is dependent on GPA plus our log2 GRE. We're going to omit rank because we decided that it was not important. Our data is equal to my data, and the family is equal to binomial. And whereas before we didn't have to specify that we were using a generalized linear model because that was in the name of the function, for the train function we need to specify that the method is generalized linear model. And now this is where we add our settings that we set a second ago with this command, where we say train control, basically what settings are we using, are equal to cross-val settings, this object here. So it passes all of these options into the train function. And if we run this, then R has performed our cross-validation. And if we have a look inside our object, we don't get an awful lot of information. We see that we have 400 samples, we have 2 predictors, and we have 2 output classes, 0 and 1. We can say that the resampling was cross-validated. There were 10 folds, and this was just repeated the one time. And then we get a brief summary of sample sizes, so that we can see that basically because this was repeated 10 times, of our 400 starting observations for each iteration, for each fold, around 360 were used as our training set, and the remaining 40 roughly were used as our test set. And then we get a value down here for our accuracy, but we'll discuss that a little bit more in a second. Now, arguably, one of the best ways to validate the predictive power of a binomial logistic regression model, or indeed any classifying model, is to look at something called the confusion matrix, which is a table which has the true positives versus the true negatives, the false positives, and the false negatives, so that we get an idea of the accuracy of our model. And we can do this by creating a new object we'll call it pred. We use this function predict. And what this function does is takes our cross-validated model, so this is the average model that was produced after performing our cross-validation, and we're going to apply this to our original data. If we have a look at pred, what it's done is apply this model, our cross-validated model, that was the average of those 10 different iterations, apply it to our original data, and use our model to predict whether each individual in my data was accepted or was accepted or rejected from their university application. And now we can use these predicted values to construct a confusion matrix. Data is these predicted values, pred, and then we just have to supply the two levels of our dependent variables, 0 and 1. So we can do that by saying my data admit, and if we hit Control and Enter, then we get a confusion matrix. So this is our matrix here, and the way that we interpret this is that this 0 and this 1 are the predicted values of 0 and 1 for our model. This 0 and 1 reference are the actual values for 0 and 1. And so these guys in the top left were actually 0, and they were predicted to be 0. So these are the true negatives. These guys were predicted to be 0, but were actually 1. And so these are the false negatives. These guys down here were predicted to be 1, but are actually 0. So these are the false positives. And these guys down here were actually 1, but were predicted to be 1 as well. So these are the these are the true positives. So I hope you can see that there are 265 correctly classified students who were rejected, and there were 111 students who were correctly classified as who were accepted and were correctly classified as being accepted. And so if we look, then in total there are 376 individuals that were correctly predicted, and there were only 24 individuals who were falsely predicted. So this model is pretty good. And then we get some more statistics down here really about, as sort of summaries of this confusion matrix. So our accuracy is 94%. So 94 out of 100 students were correctly predicted to be admitted or not by our model. And we get some 95% confidence values for that. We get a p-value for the overall model, although I'm not sure how useful that is really. And then these statistics down here are particularly useful. So the sensitivity, so the ability to detect when a person was accepted or not, when they actually were accepted, and the specificity, the ability to only categorize those that were admitted who actually were admitted. So we've constructed our binomial logistic regression model, and we've performed cross-validation. We've made sure that our sample is good enough to generalize to unknown observations, and we've evaluated our model in terms of its accuracy, its sensitivity, and its specificity. Another way that you can visually represent how good your model is at predicting group membership is by using or producing a receiver operator curve, a ROC curve. And so we're going to produce one for our model. So we're going to use the package rocker. And load it into our current R session. And we're going to use this package to visually compare the full model that we created earlier with the GPA only model. So this was the model that had GPA as a predictor only, and then our full model is the model which has both GPA and our log2 GRE as predictors. And so we're going to create an object called prob_full, probability, and we're going to use this function predict, and we're going to pass it our full model, our data, and we're going to ask it to return the response. So what this function is going to do is take the my data frame, use the full model to predict the value of admit. Okay, and then we're going to save that inside prob_full. And actually, if we call prob_full, if we call prob_full, then you can sort of see that based on a model that might perhaps be something a little bit like this, we get values of y that are predicted. And of course, if any individual value is closer to 1, then an individual will be predicted to be admitted, and if it's closer to 0, then the individual will be predicted to be rejected. And now from this, we can create another object called predictFull. And we're going to use a similarly named function, so don't get them confused, they're easily confused, called prediction. And to this, we're going to pass prob_full and the admit variable from our myData data frame. This function generates the data that Rocker requires to produce the ROC curve, and then function performance actually calculates the performance measures for our model, such as the true positive rate and the false positive rate that we'll use to create the ROC curve. So the first measure is true positive rate. The x dot measure is the false positive rate. And if we hit Control and Enter. And so we've done all this so far for our full model. And so let's just copy and paste these to save some time and typing. But rename them GPA. So change it there. Make sure that we have GPA model there. We'll call this predict GPA. Prob GPA, that's fine. Perf GPA, predict GPA. And let's run these three as well. And simply then to produce our ROC curve, just using base graphics, we could do this in ggplot, but for the sake of time, we'll just use base graphics for now. To the plot command, you simply supply the performance object. And let's add a color so that we can discriminate between them. Color equals blue, and hit Control Enter. And then our using base graphics prints a receiver operator curve for us. So the way that we interpret this is, if you imagine that instead of being GPA, this is the overall value printed out by the model, the outcome value. Exactly where along this scale we choose to set our separator determines our false positive rates and our false negative rates. So for example, let's say that this was the outcome variable of the model, and we set our cutoff at 4. And so there'd be maybe possibly 1 or 0 of these guys that would be misclassified, but actually all of these guys to the left of 4 would be misclassified as not being admitted to university. And so what a receiver operator curve does is basically takes different values, different arbitrary thresholds along the output of the model, and says at this particular value, what is the false positive rate and what is the false and what is the true positive rate. And if the line fell across a diagonal, then our model would be no better than a sort of best guess estimate. The further away from the diagonal line our model line fits, the better it is at classifying our observations. And so you can see that this particular model, our full model, is very far away from the diagonal, and so the true positive remains very, very high, whereas the false positive rate remains quite low. Now let's compare this to our GPA only model, and we can add the line on top of this plot by again calling the plot function. This time calling the GPA performance object that we created, and we'll supply this argument add equals true. And what this does is that it just prints the line on top of the plot that we already have open. So you can see it's added a black line, and the black line sits very, very close on top of the blue line for our full model. And the reason this is that although the log2 GRE variable was significant in our model and did contribute to prediction, the greatest log odds in our model, the greatest coefficient was for our GPA. Remember, it was something like 7,000 times more likely to be accepted for every 1 unit increase in GPA. Also, because of this, as long as GPA is in our model, we're still able to predict with very, very high accuracy whether a student will be accepted or rejected. Now remember, we changed the data a little bit to make the example run a little bit nicer. And so let's go back and see what happens if we didn't do that. So let's reread in the data back up here. This time, we are not going to do this. We're not going to add 1 to the GPA of students who were accepted. And instead, we're going to recreate our model. So we'll recreate the GPA model. We're going to recreate the full model. And then if we come back down here from this section on ROC, let's run this whole section again. And then let's rebuild our ROC curves. Now, because we no longer made the difference in GPAs between those students who were accepted or rejected. As large as it was, you can see that now the ROC curve is much, much closer to the diagonal line because our model is no longer as phenomenal at predicting, because now there isn't such a big difference between the GPAs of those students who were accepted and those who weren't. And if we add on top just our GPA model, then again you can see it's still quite similar because GPA was still more important really than GRE. Now, looking at the graph is a nice way of visually telling which models are better than others, but we like to have numbers to sort of quantify that. And one way that you can do this is using the area under the curve. So the greater the area under the curve, then the more accurate your model is at predicting. And we can do that by stealing this performance function from up here, copy and paste that. Let's call this AUC. Actually, let's change this to full. And this time we only want one measure, and the measure is AUC. And let's do the same, but for, we'll call this AUC GPA. Change this to GPA. And now these objects have a slightly unusual structure. So this next bit is a little bit strange, but it's just so that we can extract the AUC value. I'll show you what I mean. If I can just call this AUC object, we get a list with some names, a few different values in them, and actually this is the value that we want. To make it a little bit cleaner, we can call AUC, use the @ symbol to subset the list item that we want, and we want the y.values. And if we run that, then we get the area under the curve for the full model. And if we do the same, but for AUC GPA, then we get the area under the curve for just our GPA model. And just to note that the area under the curve, if it was 0.5, it would be exactly along the, or theoretically, it would be exactly along the diagonal line, and the model would be no better at predicting whether a student would be accepted or not than the best guess. So at least these models, although not fantastic, are better than having sort of a best guess, no information at all. Now, very finally, I mentioned at the start that we touch on multinomial logistic regression at the very end. So let's just briefly build a multinomial model. And for this, we're going to load in the iris data frame again, which is built in and comes with R. And just to refresh our memory, if we have a look at the summary, we basically have 4 continuous variables: sepal length, width, petal length, and width, and 1 categorical variable, species. And so we're going to build a multinomial logistic regression model to predict flower species from the sepal width. Now, unfortunately, we can't build a multinomial logistic regression model using the GLM function like we did for the binomial model. And so instead, we need the use of a package called nnet. So I get a warning because mine is already loaded into R. So for me, I'm just going to select cancel. If you get the same thing, you can select cancel. Otherwise, just let it install. And then we'll load nnet into our current working memory. So we're going to build our multinomial logistic regression model. We're going to call it multi-model. And this time, as I said, we can't use GLM, but we use the multinom function. We want to predict species based on, let's say, log2 sepal width. The data is the iris data frame, and if we hit Control Enter and build our model, you get some feedback that the model has finished building, and then we can summarize our model using summary. And so again, we get our model call, and we get our coefficients and standard errors, but note that we don't get any p-values, so we'll talk about that in a second. We can use, as well as looking here, we can use the coefficient function to just extract our coefficients. So again, these are log odds, which I can't interpret. So let's go ahead and take the exponent of these. And so now these are our odds ratios. Note that these odds ratios are a lot smaller than 0. And so to make them easier to interpret, we can take 1 divided by. And so let's subset this table. So let's just look at both rows of the second column. Oops. Okay, and so the way to interpret this in the case of a multinomial logistic regression model is that every time sepal width doubles, a plant is 430 times less likely to be versicolor than it is to be setosa. Every time sepal width doubles, a plant is nearly 9,000 times less likely to be virginica than it is to be setosa. Okay, so this is a slight difference between binomial and multinomial logistic regression, in that in multinomial logistic regression, no matter how many categories you have, the odds ratios are always interpreted back to a baseline, and by default this will be the one which comes first alphabetically, although you can change that manually. To explain what's going on a little bit, let's plot this data and see exactly what this relationship is. So let's plot iris, and along the bottom we'll plot species, and on the y we'll plot sepal width. And let's go with the John box plot. Oops. Sepal dot width. And so I hope this explains how we interpret the meaning of our odds ratios. Every time sepal width doubles, an individual flower, an individual observation is far less likely to belong to versicolor than it is to setosa. Every time sepal width doubles, an individual observation is far less likely to be virginica than it is to be setosa. In this case, a unit change of 1 of sepal width actually makes sense. So let's rebuild our model. I think it's probably unnecessary to log 2 these. Let's make our odds ratio slightly nicer. So if we redo this and redo this, this is perhaps slightly easier to get our heads around. For every 1 unit increase, for every 1 millimeter increase in sepal width, an observation is 454 times less likely to be part of the versicolor species than it is to be part of the setosa species. And similarly, for every 1 millimeter increase in sepal width, an individual observation is just shy of 60 times less likely to be virginica than it is setosa. And you can see that although these odds ratios compare back to setosa and not between these two, the magnitude of the odds ratio gives you some indication as to where the larger difference is. And so there's a greater difference between setosa and versicolor than between virginica and setosa. Now our multinomial logistic regression model didn't give us any p-values, and of course we all like to worship p-values, and so one way that we can get them is by installing this package AER, and if we load it into memory, we can use the function coefficient test, coef test, and supply it with our multinomial model and hit Control Enter, and then we get p-values for our odds ratios. So what we're interested in, we're not interested in the intercepts, we're interested in the odds ratios for versicolor and the odds ratio for virginica. So I hope that was useful. Binomial particularly, but also multinomial logistic regression models are very powerful models for predicting membership class and seeing the relationship between increases in certain variables and the likelihood that a person will belong to one class or the other. One reason why they're, two reasons why they're particularly popular. One of them is that clinicians like logistic regression. They understand odds ratios in the context of a clinical setting. And from a slightly more modeling and statistical point of view, logistic regression models don't care about the distribution of your predictor variables. So our sepal width, for example, could be horrendously non-normally distributed, and the logistic regression model doesn't care. Whereas if you're running something like a t-test or an ANOVA, then of course that will rend your coefficients and your p-values uninterpretable because you violated the assumption. So logistic regression doesn't have that assumption. So I strongly suggest that you play around with this data, and if you've got any of your own data, even if you have some experiments that you performed a t-test on, sort of flip your data around, include the two groups as a dependent variable, and see how the odds ratios change for an increase in your continuous variable. So I hope that was useful, and I will see you in the next video.